Light. No matter how hard you try, you cannot get rid of darkness because it does not exist. It is nothing but absence of light. In order to affect darkness, you must do something with light. Because the light is the only thing which actually exists. The more we understood about light, the more we knew about our universe. Because it exists the very beginning moment of our universe creation and time. The most weirdest, massless, fastest thing in this universe, the light. But what light is? Are we understand light properly at a very fundamental level? Where it comes from? Why it is running at a speed of 3 lakh kilometers per second? What is its relation to time, space, and matter? Is it energy, particle, wave, or something else? This film is based on light, the reality what we understand till now about light. The earliest studies about light were with understanding vision. Ancient Egyptians. The ancient Egyptians believed that light was the activity of their god Ra seeing. When Ra's eye, means the sun, was open, it was the day. When it was closed, night fell. Democritus. Democritus was an ancient Greek pre-Socratic philosopher who is primarily remembered today for his formulation of an atomic theory of the universe. He believed that the visual image does not arise directly in the eye, but the air between the object and the eye is contracted and stamped by the object seen and the observing eye. Epicurus. Epicurus was an ancient Greek philosopher and sage who founded Epicureanism. Epicurus proposed a new theory that atoms flow continuously from the body of the object into the eye. However, the body does not shrink because other particles replace and fill in the empty space. Plato. Plato was an Athenian philosopher who developed an alternate theory of vision. Plato believed that light consisted of rays emitted by the eyes. The striking of the rays on the object allows the viewer to perceive things such as the color, shape, and size of the object. Our vision is initiated by our eyes for reaching out to touch or feel something at a distance. This is the essence of the extramission theory of light that influenced for almost 1000 years until Alhazen proved it to be wrong. Light has religious importance also. Hinduism. Sun has been worshipped in Hindu religion throughout ancient times, known as the god Surya. In Rig Veda describes Surya as the golden ornament of the sky, a flying falcon, and the very countenance and the eye of the gods, traversing heaven and earth in a single day. Surya observes the whole world from on high. It is his work to dispel the dark night of ignorance and to dispense the light of life and health. Islam. The founder of the religion, Prophet Muhammad, was born there in 570 AD. And it was believed that he had received his first revelations from God in 610 AD. And the Islamic holy book, Quran, is the direct word of God. But a part of those religion belief, the real person who first tried to understand what light is was Al-Hasan, the father of modern optics, who was the greatest physicist between Archimedes and Newton and was the first person to follow the scientific method for observation of physical phenomena and their relation to theory. Al-Hasan proved the long-held theory Euclid, Hero, and Ptolemy that light originated from eye is wrong. He showed that light originated from light source. He did this by carrying out a simple experiment in a dark room where the light was sent through a hole by two lanterns held at different places outside the room. He could then see two spots on the wall corresponding the light ray originated from each lantern passing through the hole of the wall. When he covered one lantern, the bright spot corresponding to that lantern disappeared. He then concluded that light does not emit from the human eye, but is emitted by objects such as lanterns and travels from these objects in straight lines. Based on these experiments, he invented the first pinhole camera and explained why the image in the pinhole camera was upside down. Al-Hasan's theory of vision was not limited to the description of light rays originating from the objects and entering the eye. He also understood that an explanation of vision must also take into account the anatomical and psychological factors. He proved that the perception of an image occurs not in the eyes, but in the brain, and that the location of an image is largely determined by psychological factors. Sir Isaac Newton, one of the most influential scientists of all time and as a key figure in the scientific revolution. Apart from the law of gravitational force, Newton was the first who to show that the color is the property of light and not of the medium. He first understood that the light generated by sun consists of all the colors. When sunlight passes through a prism, it is dispersed in a rainbow of colors. The red color bends the least and the violet color bends the most. Newton showed that color is not a characteristic of the material, because when a particular color passed through the prism, no such dispersion took place. When all 7 colors were combined together and passed through the prism, there would be a white light, which proved that the white light consisted all the colors. Christian Huygens suggested that light is a wave and the speed of light is finite. He considered that light waves propagating through the ether just as sound waves propagate through air. He explained that the high but finite speed of light by the elastic collisions of a succession of spheres that made the ether. Thomas Young. Thomas Young was a British polymath who established the wave theory of light, in contrast to the particle theory of Isaac Newton. In 1802, Thomas Young demonstrated the wave nature of light through his double-slit experiment. He described his experiment in these words in the course of lectures on natural philosophy and the mechanical arts. And this experiment revealed the real weird secret of light. It was so beautiful experiment that in 2002, Physics World published the result of a survey on the all-time 10 most beautiful experiments in physics. Young's double-slit experiment not one, but two appearances on the prestigious list. At number 1 was a double-slit experiment applied to the interference of electron, and at number 5 was the original experiment by Young's. What was the experiment? In 1802, Thomas Young provided the first experimental evidence for the wave theory of light from the double-slit interference experiment. Young allowed the sunlight to pass through a pinhole S0 on the first screen. Then that rays followed by S1 and S2 at some distance on the second screen. On the screen, he observed a few colored bright and dark bands. To increase the brightness of bands, the pinholes S1 and S2 he replaced by narrow slits. And to increase the number of fringes sunlight, he replaced it by a monochromatic source. Finally, the interference pattern consists of equally spaced bright and dark fringes was obtained. Explanation of experiment. The spherical wave came out as the sunlight passes through the pinhole S0, as per Huygens wave theory. The radii of these waves increased as they move away from S0. When these spherical waves reached the second screen again, spherical waves came out from S1 and S2. These waves moved away from S1 and S2, and hence they superimposed on each other. At the point where wave crest or trough of one wave fell on the wave crest or trough of other, the resultant amplitude became maximum. And where the wave crest of one fell on the wave trough of other, the resultant intensity became minimum. In this way, a large number of dark and bright bands are formed on the screen. By repeating the experiment, Young related color to wavelength, and he was also able to calculate approximately the wavelengths of the 7 colors recognized by Newton that composed white light. Young's double-slit experiment played a crucial role in our understanding of the nature of light and matter even in the 20th century. The only laws of matter are those that our minds must fabricate, and the only laws of mind are fabricated for it by matter. James Clerk Maxwell. The greatest physicist you have never heard of. Every mobile phone, every television screen, and every computers we use is the same principles what Maxwell enunciated in his great papers of the 1860s. Maybe one day if we travel in time machine, which will only can possible if we understand the Maxwell demon thought experiment. So why such a great scientist has largely been forgotten? The real fundamental reason is that in his contributions that are not easily understood to the lay person as well as scientists at that time also. Maxwell had always been interested in color and light. He wanted to know why mixing different colors of light produced different results from mixing different colors of paint. Maxwell's experiments projected an image through 3 filters: red, green, and blue. Those projectors were then aligned by Maxwell to display a color image. The Maxwell color triangle formed the basis for the chromaticity chart released in 1931 by the International Governing Body on Color. Thomas Young thought that painters have a much better understanding of colors than scientists had at that time. He told that there are 3 principal colors: red, yellow, and blue. By these primary colors, we get the full color spectrum of a painting. But the theory of Newton's 7 rainbow primary colors became wrong. As Young proved, there are only 3 primary colors. And mixing all 3 fundamental colors, the new color we found, that is white. But Maxwell was Maxwell. He did not convince in Young's understanding and research what color is and why the mixing of color is different in painting and in the case of light. Because according to the painter's principal colors, he knew that blue and yellow produce the color green when mixed together. When he added blue and yellow light to his disc, the color of disc, to his surprise, did not produce green, but produced a dull pink color. And the science just waited for Maxwell for revealing God's most unexplained theory, the color. Maxwell found that blue, red, and green are the fundamental color which was tested best during his experiments. From a combination of any of these discs in the correct proportions, almost every color was created in the color spectrum. Maxwell had discovered the primary colors for light: red, green, and blue. The model comes from the initials of the 3 additive primary colors: red, green, and blue, which is called the Rgb Color Model, or an additive, in which red, green, and blue light are added together in various ways to produce a broad array of colors. The intensity of each color in the Rgb model forms a different color. When the all 3 color addition have the highest intensity, the color of light becomes white. And all this color addition having the lowest intensity, the color becomes black. And this understanding gave birth to modern electronic engineering. Each pixel on the screen is built up by the driving 3 small and very close but still separated RGB light sources. At common viewing distance, the separate sources are indistinguishable, which tricks the eye to see a given solid color. All the pixels together arranged in the rectangular screen surface conforms to the color image. Typical RGB input devices are color TV and video cameras, image scanners, and digital cameras. Typical RGB output devices are TV sets of various technologies like CRT, LCD, plasma, OLED, quantum dots, etc. Computer and mobile phone displays, video projectors, multicolor LED displays, and large screens such as Jumbotron. And what about the vision? Normally, there are three kinds of light-sensitive photoreceptor cells found in the human eye. The difference in the signals received from the three kinds of photoreceptor cells allows the brain to differentiate a wide gamut of different colors. Light enters the eye through the cornea, through the pupil, and then through the lens. The lens shape is changed for near focus, and it is controlled by the ciliary muscle, which are converted into electrical signals that are transmitted to the brain by the optic nerve and interpreted as sight and vision. The understanding of vision changed in the 20th century. From ancient Egyptians' belief, light is the activity of the god Ra, the sun seeing. When Ra's eye was open, it was the day. When it was closed, night fell. To light is a wave having fundamental colors. Apart from this, it is for his theory of electromagnetism that Maxwell is best remembered. Einstein described Maxwell's theory of electromagnetic radiation as the most profound and the most fruitful since the time of Newton. He produced the set of mathematical equations describing how classical electromagnetic fields and currents and voltages are all tied together in one beautiful symmetric framework. Maxwell's equations described how charges and currents can create electric and magnetic fields, influencing the behavior of particle movement within. Such theories of electromagnetism also accounted for how light moves through a vacuum without the assistance of a helpful medium like the ether. Let us understand the matter. Maxwell gave a classical picture of light as consisting of electric and magnetic waves. This was a truly remarkable outcome of his efforts to unify the two known forces of nature, electric force and magnetic force. According to Michael Faraday, a time rate of change of magnetic field yield electric force. So Maxwell thought if electricity and magnetism were the two sides of the same coin, then a change of electric field should similarly result in a magnetic field. In 1865, Maxwell showed that electric and magnetic fields travel through space as waves moving at the speed of light. Working on the problem further, Maxwell showed that the equations predict the existence of waves of oscillating electric and magnetic fields that travel through empty space at a velocity of 31,740,000 meters per second. In his 1864 paper, A Dynamical Theory of the Electromagnetic Field, Maxwell wrote, "The agreement of the results seem to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. Or we can say light itself is an EM wave." Maxwell shocked the physics world by unifying electricity, magnetism, and light and postulating that they were all the same type of physical phenomena, the electromagnetic waves or radiation. Electromagnetic waves are waves that propagate or radiate amongst the electromagnetic field. Some examples of electromagnetic waves include visible light, X-rays, radio waves, gamma rays, and ultraviolet rays. Maxwell equations combine electricity and magnetism using advanced calculus and are taught in upper-level physics courses. These equations are: Maxwell's equations have been praised as the second most important unification in field of physics after Newton's equation. But what was the understanding we got from Maxwell? In physics, what is electromagnetic radiation? Electromagnetic or EM radiation is a form of energy that is all around us and takes many forms, such as radio waves, microwaves, X-rays, and gamma rays. Sunlight is also a form of electromagnetic energy, but visible light is only a small portion of the electromagnetic spectrum from a broad range of electromagnetic wavelengths. Before going to more depth, we should know few fundamental things. There are 4 main electromagnetic interactions. Number 1, the force of attraction or repulsion between electric charges is inversely proportional to the square of the distance between them. Number 2, magnetic poles come in pairs that attract and repel each other, much as electric charges do. Number 3, an electric current in a wire produces a magnetic field whose direction depends on the direction of the current. Number 4, a moving electric field produces a magnetic field and vice versa. How electromagnetic radiation is created. Electromagnetic radiation is created when an atomic particle, such as electron, is accelerated by an electric field causing it to move. The movement produces oscillating electric and magnetic fields which travel at right angles to each other in a bundle of light energy called light. Light travels in harmonic waves at the fastest speed ever possible in this universe. That is 186,282 miles per second or or 299,792,452 meters per second in a vacuum, also known as the speed of light. The waves have certain characteristics given as frequency, wavelength, or energy. A wavelength is the distance between two consecutive peaks of a wave. This distance is given in meters or fractions thereof. Frequency is the number of waves that form in a given length of time. It is usually measured as the number of wave cycles per second or hertz. A short wavelength means that the frequency will be higher because one cycle can pass in a shorter amount of time. Similarly, a longer wavelength has a lower frequency because each cycle takes longer time to complete. The EM spectrum. EM radiation spans an enormous range of wavelengths and frequencies. This range is known as the electromagnetic spectrum. The electromagnetic spectrum is generally divided into 7 regions in order of decreasing wavelength and increasing energy and frequency. The common designations are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Typically, lower energy radiations such as radio waves is expressed as frequency. Microwaves, infrared, visible, and UV light are usually expressed as wavelength. And higher energy radiations such as X-rays and gamma rays is expressed in terms of energy per photon. According to Maxwell's equations, a spatially varying electric field is always associated with a magnetic field that changes over time. Likewise, a spatially varying magnetic field is associated with specific changes over time in the electric field. In an electromagnetic wave, the changes in the electric field are always accompanied by a wave in the magnetic field in one direction and vice versa. This relationship between the two occurs without either type of field causing the other. Rather, they occur together in the same way that time and space changes occur together and are interlinked in special relativity. Ultraviolet. Ultraviolet light is in the range of the EM spectrum between visible light and X-rays. It has frequency of about 8 into 10 to the power 14 to 3 into 10 to the power 16 Hz and wavelengths of about 380 nanometer or 0.00015 inches to about 10 nanometer or 0.0000004 inches. UV light is a component of sunlight. However, it is invisible to the human eye. It has numerous medical and industrial applications, but it can damage living tissues. Radio waves. Radio waves are at the lowest range of the EM spectrum, with frequencies of up to about 30 billion Hz or 30 gigahertz, and wavelengths greater than about 10 millimeters or 0.4 inches. Radio is used primarily for communications including voice, data, and entertainment media. Microwaves. Microwaves fall in the range of the EM spectrum between radio and infrared. They have frequency from about 3 GHz up to about 30 trillion Hz or 30 terahertz, and wavelengths of about 10 mm or 0.4 inches to 100 micrometers or 0.004 inches. Microwaves are used for high bandwidth communications, radar, and as a heat source for microwave ovens and industrial applications. Infrared. Infrared is in the range of the EM spectrum between microwaves and visible light. Infrared has frequencies from about 30 terahertz up to about 400 terahertz and wavelengths of about 100 micrometers or 0.004 inches to 740 nanometers or 0.00003 inches. Infrared light is invisible to human eyes, but we can feel it as heat if the intensity is sufficient. But what about visible light? Visible light. Visible light is defined as the specific wavelengths electromagnetic force that are visible to most human eyes. In fact, color is a property of light and an artifact of the human eye. Objects don't have any color. Rather, they give off specific wavelength light that appears to be a color. In other words, color exists only in the mind of the beholder. Visible light is found in the middle of the EM spectrum between IR and UV. It has frequencies of about 400 terahertz to 800 terahertz, or about 4 multiplied by 1014 to 8 into 1014 cycles per second, and wavelengths of about 740 nanometers or 0.00003 inches to 380 nanometers or about 0.00015 inches. Light at the lower end of the visible spectrum, having a longer wavelength, about 740 nanometer, is seen as red. Light in the middle of the spectrum is seen as green, and light at the upper end of the spectrum with a wavelength of about 380 nanometer is seen as violet. All other colors that we perceive are mixtures of these colors. For instance, yellow contains both red and green. Cyan is a mixture of green and blue, and magenta is a blend of red and blue. While light contains all colors in combination, black is a total absence of visible light. Air scatters blue light more than red light, and so the midday sky appears blue, apart from the area around the sun, which appears white because the light is not scattered as much. Many species can see light within frequencies outside the human visible spectrum. Bees and many other insects can detect ultraviolet light, which helps them find nectar in flowers. Plant species that depend on insect pollination may owe reproductive success to their appearance in ultraviolet light rather than how colorful they appear to humans. Birds too can see into the ultraviolet, that is 300 to 400 nanometers. Most mammals are diachromatic, and dogs and horses are often thought to be colorblind. They have been shown to be sensitive to colors, though not as many as humans. Some snakes can see radiant heat at wavelengths between 5 and 30 micrometers, such that a blind rattlesnake can target vulnerable body parts of the prey at which it strikes. And other snakes with the organ may detect warm bodies from a meter away. It may also be used in thermoregulation and predator detection. Color relation with temperature. As objects grow hotter, they radiate energy dominated by shorter wavelengths, which we perceive as changing colors. For example, the flame of a blowtorch changes from reddish to blue as it is adjusted to burn hotter. At about 800 degrees Celsius, the energy radiated by an object reaches the infrared. As the temperature increases, the energy moves into the visible spectrum and the object appears to have a reddish glow. As the objects get hotter, the color changes to white hot and eventually to blue. Visible light astronomy. The color of hot objects, such as stars, can be used to estimate their temperatures. For example, the sun's surface temperature is about 5,527 centigrade. The light emitted has a peak wavelength of about 550 nanometer, which we perceive as visible white light or slightly yellowish. The star Betelgeuse, it would look reddish because surface temperature were cooler, about 3000 centigrade. Star Rigel is hot about 12,000 centigrade, so it looks blue. Astronomers can also determine what objects are made of because each element absorbs light at specific wavelengths called an absorption spectrum. By knowing the absorption spectrum of elements, astronomers can use spectroscopes to determine the chemical composition of stars, dust clouds, and other distant objects. So till the end of 19th century, we understood that visible light is a fraction of electromagnetic radiation or visible spectrum that we can see with our eyes. Right to the visible spectrum, we found the type of energy that are lower in frequency and longer in wavelength. This type of energy includes infrared rays or heat waves given up by thermal bodies, microwave, radio wave. This type of radiation surrounds us constantly and are not visible and harmful because their frequencies are so low. Left to the visible spectrum, we have ultraviolet, X-rays and gamma rays, which have extremely high frequencies and high energy and are dangerous for a living creature. This is all about light, which is understood by scientists in 20th century. But in 21st century, the understanding of light is changed due to quantum theory. Please see my next film, Light Part 2, to understand light in 21st century. This is all for now, and please don't forget to like, share, and subscribe my channel, and bye-bye.